Okay, number 2 on the Fourier response, we need to find a power series representation for ln of 1 plus x. And it gives you the hint in this problem that we're going to use the power series that we know for 1 over 1 minus x. So let me write that up here real quick. Remember, we know that this power series is equal to 1 over 1 minus x for the interval -1 to 1, where x is in -1 to 1. So we need to figure out what's going on here. How can we get that out of this? So first of all, what we're going to want to do is see that you can write this instead as 1 minus -x. And then let's see what happens when you take the derivative of that. So when you take the derivative of ln of 1 plus x, again, when I do this, I'm going to be writing in this form just because that's easier to take the derivative of. Whenever you take the derivative of a natural log, remember that you're going to get 1 over that times the derivative of the inside, but in this case, the derivative here is just 1, so we don't have to worry about the chain rule. And by doing this same transformation as we did here, so if we take the derivative of what we want, we get something that we know, which means that we need to take the antiderivative of the thing we know, we'll get what we want. So we need to figure out, but it's not exactly the thing we know. We have replaced x with -x. So we're going to do this now with the series. So we're going to start with just this, the series x to the n power. What do we need to do? We need to replace every instance of x by -x. So this is x goes to -x. That gives us the series -x to the n, which could be rewritten as, it's just the alternating version of x to the n. Keep in mind, you want to do that generally before you do any differentiation or integration, because this is now just a constant and you don't have to worry about it. So what was the last thing we needed to do? We needed to integrate this, because then, remember, we were trying to get ln of 1 plus x. We figured out that if we took the derivative of this, we get what we want. So if we have to take the integral of this, we'll get back to this. So now we're going to do the integral, the antiderivative here of this. So what do we get? N equals 0 to infinity. We still have it as alternating. And now instead of x, we have x to the n plus 1. Excuse me, over n plus 1. So now this is our series. This is equal to ln of 1 plus x. Let me write that there. So the one thing we need to ask ourselves before we cement that as an answer is, is our interval still -1 to 1? Well, differentiating and integrating does not change your interval. We did, however, do a substitution for x. We turned x into -x. So that means that instead of x being in -1 to 1, we actually have -x is in between -1 and 1. But if you think about that for a second, if -x is in between -1 and 1, that's the same thing as x being between -1 and 1. So we actually do have the same interval. But remember, anytime you do a substitution for x, you have to consider that your interval may have changed. So this is our series here. So that was part A. In part B, what are the radius and interval of convergence? Well, that was what I was just talking about. Our radius is still 1. Our interval is the same, -1 to 1. Like I said, though, always make sure you check that if you did a substitution for x. And part C finally says use the first 2 terms of that power series to approximate the value of ln of 1 plus 1, or 1.1. So let me write that part over here. So we want to approximate ln of 1.1 by using the first 2 terms of this. So the first two terms are going to be the n equals 0 and the n equals 1 terms. Well, these can be pretty simple here, so let's just figure out what that is. If you plug in n equals 0, negative 1 to the 0 is positive 1. We would have x. And on the denominator, we would have 1, so we just have x. So the first term is x. The second term is now when n equals 1. That would make it negative, so we're going to have minus. Now, instead of x, we have x squared, and on the denominator, we have 2. Okay, so these are the first two terms of this series. So we want to approximate the value of ln of 1.1. So here's the last kind of tricky part about this problem. 1.1 is not what we plug in for x, because what was our function? Our function is ln of 1 plus x. So if we're trying to approximate 1.1 from this, what is x? Well, x is 0.1, because 1 plus 0.1 would give us 1.1. In other words, x is 1/10. So now we can figure out what our approximation is by just plugging that in. So we get 1/10 minus 1/10 squared would be 1 over 100 over 2. In other words, 1/10 minus 1 over 200. If you get a common denominator here, this would just be 20 over 200. So finally we get 19 over 200 is our approximation using the first two terms.